Hey everyone, let's discuss dependency preservation. In previous lecture, I already discussed lossless decomposition. After decomposition, the data, the dependency should not be lost. That is lossless decomposition. If we are losing the data, then that is a lossy decomposition. What is dependency preservation? After decomposition, the functional dependency should preserve. Okay, means the attribute of LHS and RHS of a functional dependency should be in one relation. Suppose we have set of functional dependency F for relation schema R. Now after decomposition we got R1, R2, Rn. Now the restriction of F to Ri is the set of Fi of all functional dependency in F positive closure that includes only attribute of Ri. Let's understand through an example. Let we have a functional dependency A implies B, B implies C, and we have a decomposition AC, AB. Now, according to this functional dependency, A, B are in one dependency, B, C are in another dependency. So, A, B and B, C should be in one relation schema. Suppose R1 contain A, B, R2 contain B, C, we can say dependency is preserved as BC is from one functional dependency, AB from one functional dependency. But here we did decomposition as AC and AB. AB that is in one functional dependency, so dependency preserved. Is AC dependency present? A implies B, B implies C. According to transitive rule, A implies C. So A implies C, that functional dependency exists. If we find F positive closure, we are getting A implies C. Hence, AC decomposition also possible. So, the restriction of F to AC include A implies C. Since A implies C is in F positive closure, even though it is not in F, we can use that decomposition. Let F dash equals to F1 union F2 union till Fn. So F dash is set of functional dependency on schema R, but in general F dash not equals to F. Means from F we are getting lots of additional functional dependency that included in F dash. F dash is not equals to F, but if we'll find positive closure, F dash positive closure equals to F positive closure. We can say dependency preserved. That decomposition is preserving the dependency. In simple way, you can say F positive closure equals to F1 union F2 till Fn positive closure. This is nothing our F dash, where F is the functional dependency for relation schema and F1 is for R1, F2 is for R2, Fn is for Rn. So if one dependency is not present in F and it's present in F positive closure, then also we can do that decomposition. Simple way, just check LHS and RHS are present in one relation or not. That is the basic, not including the F positive closure. After finding the F positive closure also, for the additional functional dependency, you can check LHS and RHS are in same table or not. Let's see some example. Example 1, A implies BC, B implies DE, D implies E, FG implies A. Now, R1 equals to ABC. Here A, B, C are in one functional dependency, so dependency preserved. R2 equals to B, D, E. Yes, B, D, E are in one functional dependency. Then D implies E. D implies E also in R2. Then FG implies A, that is in R3. Next, R4 AB. AB is in this functional dependency. Hence, dependency is preserved. So R1 and R4 come from A implies BC, R2 is for B implies DE and D implies E, R3 is for FG implies A. Here dependency preserved as all functional dependency are in one relation. Next example 2, B implies C, D implies A, and we have two relation schema BC, AD. Here dependency is preserved, but it's a lossy decomposition. If we'll make the table for checking lossless, then R1, R2, A, B, C, D. So B, C, A, D. In last row, all attributes are not there. Hence, it's a lossy decomposition. Dependency is preserved, but it's a lossy decomposition, hence it is a bad decomposition. Next, example 3, AB implies C, C implies A, C implies D. So R1 contain BC, R2 contain ACD. CA, CD, these two are here. Then A, B, C, that should be in one relation. Here just BC is there. Here dependency is not preserved, but it's a lossless decomposition. Here B, C, then A, C, D. You can write B. So A, B, C, D all we are getting in last row. Hence this is a lossless decomposition, but dependency is not preserved. AB implies C, dependency is not preserved. C implies A, preserved in R2. C implies D, preserved in R2. But AB implies C, that is not preserved. This is a lossless decomposition, but as dependency is not preserved, hence bad decomposition. For good decomposition, it should be lossless and dependency preserved. If either one is missing, either it is a lossy decomposition or dependency is not preserved, then it's a bad decomposition. In today's session, I discussed what is dependency preservation. In next lecture, I will discuss BC and F. I already discussed 1NF, 2NF, 3NF. Just go through previous lecture. And if this lecture is helpful for you, please like, share and subscribe. Thank you. Bye-bye.